This paper presents a novel key points-based method to control the configuration of a robotic manipulator in image space using an adaptive image-based visual servoing scheme. In existing literature, image-based visual servoing in an eye-to-hand setup control the end effector on the image space using specialized markers like Arupo. In this paper, we aim to remove the constraints of external markers and propose a novel method to use purely natural visual features on the robot's body to control the robot in configuration space. In our prior work, we used control points of a B-spline curve as natural features along the robot's body to control the robot configuration in the image. This is the state of the art for using multiple image features along the robot's body in an image-based visual servoing scheme in an eye-to-hand setup. We use depth image to extract the skeleton of the robot to fit the B-spline. However, due to inconsistencies in the depth images, the skeleton tends to be unstable, which led us to use fiducial markers to restrict the skeleton. To make the features purely natural, we took inspiration from the key point detection approach to solve human pose estimation problem in computer vision. In this problem, key points are the pixel coordinates of a point on a human body part in an image annotated in large data sets like COCO, which are then used to track different human poses using deep learning architectures like OpenPose. In our proposed method, we identified and annotated 10 key points and bounding boxes on the robot. In order to identify the key points, we combine camera parameters and the individual joint positions on the arm in the world coordinate system to project the 3D joint location indicated here as PW on the image space indicated as P, which is the key point annotation for our dataset. We repeat this for several configurations of the arm to create a data collection pipeline. We customized Torch Vision's key point RCN in Breastnet 50 FPN network and trained the collected data. The inferred key points along the robot's body are then used to define the image error between the current and desired robot configuration as shown in equation 1. We obtain the joint velocity QR dot in equation 2 by combining a control gain lambda, the image and robot Jacobian, and the image error. The combined robot and image Jacobian referred to as JC hat is estimated online. We determine a window size and the update law in equation 4 updates JC hat for each window using the correction term in equation 5. For our experimental setup, we used a Franca Amica Panda arm and an Intel RealSense D435i camera in an eye-to-hand setup. We conducted 18 experiments to variable goal configurations in planar space using 3 natural features on the robot and compared the performance with our prior skeleton-based method. Our method results in faster convergence due to less noisy and more robust features. We measured rise time, settling time, and overshoot as our performance metrics for both proposed and existing methods and observed a minimum of 20% improvement in all the categories in our proposed method. To assess the repeatability of our proposed method, we repeated 5 experiments for the same initial and reference configuration. The measured variance is negligible. Using our approach, we were able to servo the arm in different configurations, even at the edge of the robot's workspace, with smooth trajectories and minimal noise. We were able to achieve servoing in 3D space only using visual features with our method as a proof of concept. However, the control gains applied were not stable and needed to be freshly tuned for each control experiment. To summarize, our proposed method used natural visual features without any markers to control the robot configuration. It is robust to unknown robot model and no encoded information was used during control. Our method is faster in transient response with lower overshoot compared to the state of the art. The QR code has the link to our open source data collection pipeline. As a future direction, we need to work on controlling the arm in 3D Cartesian space and also handle occlusion during control.